This video will focus on both weak and strong acids and bases, understanding which ones are weak versus strong, understanding how to write equilibrium expressions for weak acids and bases, and then also starting to look at the math behind weak acids and bases. So I thought I'd post this list again for you guys since you know you have to memorize these. The bases aren't so bad because they're all the alkaline metals. The acids, though, you may have to memorize. I'm not really sure, but make sure you do know them because the math is totally different if you're using a strong acid versus using a weak acid, or a strong base versus using a weak base. So again, what do we mean by strength? By strength, we don't mean concentration. So a 1 molar solution isn't stronger than a 0.1 molar solution, for example. When we talk about a strong acid, what we're talking about is the degree of ionization. Strong acids ionize more, meaning they break up into solution more, producing more H's in the solution. Right? A weak acid ionizes less, meaning as you put it into solution, not a lot of the acid actually ionizes into the H plus and the conjugate base. Okay? If we looked at this from the base perspective, we could do the same thing. Weak bases just don't dissociate as much, don't make as much OH in solution per amount of stuff. Meaning, again, if you had a 1 molar solution of hydrochloric acid, which is a strong acid, and you had a 1 molar solution of acetic acid, which is a weak acid, they would not have the same amount of H plus in solution, okay? While they are the same concentration in terms of the amount of the hydrochloric acid or the acetic acid put into solution, the hydrochloric will make more H plus, making it a stronger solution in terms of the reactivity. We can quantify that strength using the acid dissociation constant. So the degree to which it dissociates is a constant, right? The K, the same as the solubility constant and your water constant. This is the measure of how much it dissociates. Okay? If you have a Ka that is greater than 1, that's considered a strong acid. So that means that more of it is dissociating than isn't dissociating, which would mean it's strong. A general expression for an acid dissociation constant is given on the screen. Ka, which is the acid dissociation constant, is the concentration of the dissociated ions multiplied together, so the A minus and the H plus, divided by the concentration of the actual acid put into solution. And then there's a note here. If you have a polyprotic acid, each H plus will have its own dissociation constant and its own dissociation equation because you go through it one step at a time as the H's come off. So where does this general equation come from? Well, if you have any acid, Ha, it's going to dissociate into H plus and A minus. That's how it falls apart, right? And a constant, the dissociation constant, is always the concentration of the products divided by the concentration of the reactant. Now, we're used to not writing this for solutions because that's a solid, but in this case, this is kind of weird, this is in solution. Okay, it's still considered to be part of the solution, so it is considered part of the equation. If this were water, which is a liquid, then we wouldn't use it. But this is considered aqueous in that it's in solution, it just hasn't dissociated. It's kind of like sugar. You can have sugar in solution, but it doesn't dissociate into ions. This is dissolved into solution, but it didn't dissociate into its ions. So this is still considered aqueous, and it would still be part of your equilibrium expression. So on the screen now you have examples of specific dissociation equations for different weak acids. And you can do this for strong acids too, but these are specifically for weak acids. So let's look at one of the specific examples. If we're looking at the second protonation of sulfuric acid, so the second hydrogen dissociating, it's going to dissociate into one hydrogen coming off, and then you'll have the other ion, and it goes to a -2 because the H came off, so you have an extra charge there. So this is the dissociation equation. The Ka for this then is the concentration of that H plus times the concentration of the SO4 minus 2 all over the concentration of the original acid. Okay, so that's a dissociation. K is a constant, right, which means it's a known variable for all of these things. There are tables of them. We can always look up the Ka for any weak acid we may be dealing with. But what this is going to allow us to do is when given the concentration of the acid put into solution, you can then calculate the amount of hydrogen that dissociates, and that is our relationship with pH. Right? So far we've been able to say concentration of this is concentration of this, and that's how I've calculated pH. But for a weak acid, these two variables are not the same because it doesn't fully dissociate. Okay, so here you can see how knowing whether you're dealing with a strong acid or a weak acid is really important, because you will have to do a Ka expression to calculate pH of this, where for a strong acid, you can just pop it into the equation and be done. So we can try another practice problem here, writing Kas for phosphoric acid. So phosphoric acid is H3PO4. When it dissociates, one hydrogen will come off. That's its first protonation level, which means you'll have two hydrogens left behind with a charge of -1. So the Ka for this then would be the concentration of H plus times the concentration of H2PO4 divided by the concentration of that initial acid. If you want to for practice, you can do the second protonation and the third protonation, taking off more and more hydrogens, which all have their own Ka expression, and we'll do a couple more examples in class 2.